All right, carboxylic acids, as we have mentioned, are fairly stable, and they've got a big problem is they don't like to do nucleophilic acyl substitution reactions, and the reason is simple. Acyl substitution requires more stable products, which comes from a stronger base. We need the nucleophile that is attacking to be a stronger base than the leaving group. But the two things, one thing right here is if we're going to consider the leaving group here, OH minus would be a leaving group. Well, OH minus is hydroxide, strong base. It's a horrible leaving group. That's one problem. But we have an even bigger problem. What is the second word in the functional group carboxylic acid? That's right, it's an acid. This hydrogen here is fairly acidic, pKa of 4 to 5. So any decent nucleophile is going to also be a decent base, and it will react with this hydrogen and deprotonate the carboxylic acid instead of attacking the carbonyl carbon. And this is a problem because O minus is a horrible, absolutely horrible leaving group. It becomes O2 minus if it tries to leave oxide. Extremely strong base. So carboxylic acids really just do not do nucleophilic acyl substitution. But we want them to do it. I've got a carboxylic acid and I want to turn it into something that we can do substitution with. Okay, easy. Use our good old friend thionyl chloride, SOCl2. Recall that takes any OH and turns it into Cl. So a carboxylic acid react with thionyl chloride makes an acid chloride. Plus SO2 and HCl, and who cares about that? We've got an acid chloride, our most reactive RCOZ compound that we're currently looking at. So, thionyl chloride, you gotta love it, takes a carboxylic acid, one that will refuse to do nucleophilic acyl substitution, and turns it into an acid chloride, our most reactive molecule towards nucleophilic acyl substitution. I'm not worried about the mechanism here if you want to know about it. I just worried about, hey, you see the carboxylic acid, you see thionyl chloride, you now have an acid chloride, and now you can do any reaction you want to. Nucleophilic acyl substitution, that is. All right, and note, this is kind of cool. This reaction, it's not the easiest to do, but if you have something like succinic acid, a dicarboxylic acid here, and those two are connected, if you heat this up strongly enough, and we were talking about pretty strong here, you can dehydrate the reaction. We get rid of H2O. Well, if these two hydrogens and this oxygen is gone, this oxygen remains, and now we form a bond between it and that other carbonyl. We won't look at the mechanism here, but you can make succinic anhydride by this reaction. But let's think about this. What's more stable, carboxylic acids or anhydrides? Yeah, carboxylic acids are more stable than anhydrides here. Note we've got the carbonyl, oxygen carbonyl. It's an anhydride. This is a much less stable compound than this is. So the only way to get this to work is really heat it up for probably going to take a little while. But you got to drive off that water. The only way to get this work is make sure this water is driven off such that the reverse reaction cannot occur. Because succinic anhydride and water, just under normal conditions, will form succinic acid really nicely. So this is a tough reaction to do. We got Le Chatelier the crud out of it. Get that, because Le Chatelier's principle, if we get rid of this water, we get rid of one of the products, then the equilibrium has to shift to make more of this to try to make more water, which will continue to get rid of. So it's a tough one, but I guess it can happen. All right. So then what reactions can we do with carboxylic acids? Well, here's a way we can do a nucleophilic acyl substitution. Fischer figured out, he did this, he did an esterification, and now we call it a Fischer esterification. Because Fischer and people looked at it and did isotopic labeling studies to figure out the exact mechanism, what they found out, if you take a carboxylic acid and an alcohol, you react it with sulfuric acid, H2SO4, you will get the ester and water. Now the question was, okay, this water, where did the oxygen in the water come from? Is the oxygen, did it come from the carbonyl, or did the oxygen come from the alcohol? Did it come from the carboxylic acid or the alcohol? Where did this oxygen come from? And what Fischer did with his labeling studies was show that if you took a normal alcohol, or excuse me, a normal carboxylic acid, but you had an alcohol labeled with oxygen 18. Now, oxygen 18 is radioactive, which you have O18 in this alcohol, which means this is radioactive. You hold up a Geiger counter, it'll beep every once in a while. It'll beep because this oxygen is radioactive and it's decaying. And so, okay, we've got our organic product here. We've got our alcohol here. We add H2SO4. Note we get this ester, and as long as our R groups are fairly large, like 3 or 4 carbons each at least, then this is not going to be very soluble in water. But we also get water, which means we'll get 2 layers. And the question was, okay, after separating the 2 layers, did the beeping, was the O18 in the organic layer or was it in the aqueous layer? And Fischer found it was in the organic layer, which said, okay, if these 2 react, but this OH ends up on this, or this oxygen ends up on this carbon, the carbonyl carbon in our final product, how does that occur? What is the mechanism? And what Fischer reasoned out was the mechanism. Part 1, when you had our sulfuric acid, it's the catalyst. You just mix the alcohol and the carboxylic acid, nothing happens. But you throw in this sulfuric acid catalyst, and the carbonyl oxygen, the double bonded oxygen, attacks the hydrogen of sulfuric acid, a protonation reaction, to give us this positively charged oxygen with the hydrogen on it. The alcohol then comes in and attacks the carbonyl carbon, breaking the pi bond, and those 2 electrons go on the oxygen here. So now we have the OH here that was once the carbonyl, and the hydrogen from the sulfuric acid. We've got our original OH is right here. And now we've got our alcohol, R18H, R single bond O18H. Right here, note this is an oxygen with 1 lone pair and 3 bonding pairs. That's a positively charged oxygen when you do the formal charge. Okay. And then note we also made this HSO4 minus, the conjugate base of sulfuric acid. It comes back in, takes this hydrogen to reform sulfuric acid, because note, sulfuric acid is our catalyst. In catalyst A speeds up the reaction, B, you have to remake the catalyst. So this HSO4 minus comes in and snags this hydrogen. So now we've got our 2 OH groups on here and our OR group on here from our alcohol that attacked. And we still have sulfuric acid in there too. Okay. So note the point of the sulfuric acid in this step was if you just mix this carboxylic acid and alcohol, there's not going to be any reaction because this is a neutral nucleophile. The oxygen here is neutral. And this carbonyl carbon has partial positive charge to it, but it's just not enough partial positive, just not enough positive charge to really attract that oxygen. But if you protonate that oxygen, you can see that this beast right here, see how we have carbon double bond OH, carbon single bond OH? This has resonance forms. We could have easily moved the double bond down here. Note, we could also have just broken the pi bond, made 2 neutral OHs, and made this carbon have the positive charge. Through the resonance, we delocalize positive charge onto this carbon here. So once we have protonated this oxygen, this carbon becomes more partially positive charge through resonance than it was before. And now that this carbonyl carbon has much more positive charge to it, now it's more attractive to our neutral oxygen, and now the neutral oxygen will attack it. So that is how the sulfuric acid speeds up the reaction. By protonating the carboxylic acid, it makes the carbonyl carbon more positively charged, which means the oxygen here is more likely to attack it. Okay, and with a deprotonation here, we get our sulfuric acid back. But note, at this point, we've got two OHs and an OR on here. We're not to our ester yet. Part 2 is, okay, now we've got this beast. We've got our, I don't know, this diol OR thing here and O18 on here. Now, we've got our H2SO4. It got regenerated in this step. One of these oxygens will attack the H2SO4 to protonate this, and we've recognized this from organic 1. This is a good leaving group. So a lone pair will come down, form a bonding pair to this carbon, kick off that good leaving group water, elimination of H2O, and then our SO4H- will come back in, this hydrogen to give us our ester. Our H2SO4, we get our acid catalyst back again. We generated the water in this step. We got rid of this water here. Okay. So that's the Fischer esterification. Note, this is 1, 2, 3, 4, 5, 6. This is a 6-step mechanism. That's pretty tough to figure out, especially in Fischer's day when they weren't looking at NMR and that type of stuff. They're just doing rate studies and isotopic labeling studies. Now, the thing to remember is, as nasty as this mechanism looks, as nasty as it is, if you're actually running the reaction, a Fischer esterification in the lab, what do you have to do? How do you get this mechanism to work? The answer is, you take a carboxylic acid, you mix it with an alcohol, you add sulfuric acid, and you wait a little bit, and then you get your ester. That's all there is to it. As an experimenter, this is easy. In fact, you either have done or will do this reaction, Fischer esterification. This is benzocaine. When we made benzocaine, it was a Fischer esterification reaction. And all you had to do was throw the two together, throw in some acid, let it run for about an hour or so, and bang, you got your product. And if you recall, benzocaine reaction worked pretty well. So, Fischer esterification. One last thing here. When we get to this point right here, on part 2, note we said this OH takes this hydrogen to protonate this. Well, couldn't this OR have taken the hydrogen? Couldn't we have protonated this oxygen down here? And the answer is yes. I mean, this OH could have been protonated. Well, that's the same as this OH getting protonated, but this OR could have been protonated. And the truth is this OR does get protonated sometimes, but that is just the reverse reaction of this step. If we protonate this oxygen down here that has the R group on it, we just go back to here. And where do we go from here? Well, we go back the other way. So these are reversible. These reactions are reversible, but in driving this forward, it is this hydrogen that gets protonated. This OH that gets protonated here. Okay. Now, because it is reversible, we might have to Le Chatelier this. Note that water gets formed here, and so the more you can do to get rid of water, the less water you have around, the more likely this is to go to the right. There's nothing crazy we needed to do here for the reaction. Just heat it up and make sure all of our reagents were very, very dry. Concentrated sulfuric acid. Note our alcohol we added was anhydrous. It was absolute ethanol, not 95%, because 95% ethanol has 5% water. No, we added absolute ethanol, no water around, and that made sure that there wasn't much water around to make sure that the reaction went all the way to the right here. All right. Note, you can also do, if you wanted, an intramolecular esterification. Here we're going to do a Fischer esterification, but note our carboxylic acid and our alcohol are connected together. They're part of the same molecule. But hey, if we've got a carboxylic acid, we've got an alcohol, and those two are close enough together that this CH2 right here could bond to this OH. Just have to throw in a little H2SO4, and we'll get a Fischer esterification. This carbon ends up bonding to that oxygen, and there we go. Although we have found that it's really the oxygen of the alcohol that ends in here, it's really the carbonyl gets bonded to this oxygen, right? Yeah, it is the carbonyl will get protonated, and then this oxygen will attack that protonated carbonyl, and eventually this guy will leave as water. So it's this oxygen bonded to that carbonyl. As long as the chain is long enough to do that, there you go. Note, it's an ester, it's a cyclic ester, alpha, beta, gamma, delta, a delta lactone. All right. Converting a carboxylic acid into an amide. This would seem pretty straightforward. Don't you just react the carboxylic acid with an R2H, just the amine? Turns out that's not going to work very well usually, because note, if we have a carboxylic acid and we have a base, the base is just going to react with this protonated hydrogen. Yeah. So any good nucleophile is going to just do this deprotonation reaction. However, what we have found, and this is nasty, this is a tough one, but if you add that base, you make our carboxylic acid and NH4 plus salt here, do our acid-base reaction. If we heat this up greater than 100 degrees Celsius, means we can drive off water. We can actually drive off this oxygen and 2 of these hydrogens here to give this nitrogen bonded to the carbonyl and the 2 hydrogens bonded to the oxygen, get this amide and H2O. Very low yields. This is a brute force way of doing it. There is a better way of doing it. We are going to combine a reaction. We're going to combine this with DCC, dicyclohexyl carbodiimide, a dehydrating agent. It turns out this beast here, this dicyclohexyl carbodiimide, really loves water. So whenever this thing finds water, it's just going to snag that water really, really quickly. The equilibrium constant for this reaction lies way, way, way to the right, which means if you throw this in with this reaction up here, this reaction doesn't go very nicely. A little bit of water will be made, but if you've got this dicyclohexyl carbodiimide in there, it's going to take that water. Even that tiny bit of water that gets made, this is going to react with it. And Le Chatelier's principle says, well, then we need to reestablish the equilibrium to make a little bit of water that got taken away. We need to replace it. So the reaction replaces that little bit of water that got taken away by just going ever so slightly towards products. But then our DCC takes that water too. So the reaction has to go and make a little bit more water. You can actually get this reaction to go nearly 100% and make all this product if you add enough DCC, because any water that gets made, and a little bit will always get made due to the equilibrium, we just take it away, and so Le Chatelier's principle tells us that the reaction has to shift to make more of this product. So that's a way to get this reaction that shouldn't work and doesn't work with heat to get to actually work pretty well. Good old Le Chatelier. All right. Let's see. Okay. Let's, looking at this, let's just, this is getting a little long. Let's end the video here. Our next video is going to be esters, and that's the last one we're going to look at, I believe, for, that next video will be a little bit short.